10. Okay, and again, these two chapters, chapter 10 and 11, are going to be on the exam coming on the 20th of September. Okay, so for a quick review, so for the last couple of lectures, so we went over these kind of things right here. We looked at the transfer function, and since it's complex, we can break it apart into a magnitude and also a phase, right? And we get a Bode plot from those kind of things. We looked at the low-pass filter, its characteristics, high-pass filter, the band reject type of filter, and compared it to the band pass filter, and also active filters adding in op amps for those characteristics. And basically, these are can also be used as building blocks for filters as well. For the last lecture, we looked at how to plot in MATLAB. Okay, here's like the basic functions right here. Okay, you want to define your log space and the number of points. Here's your transfer function right here. And then from that, you get your magnitude, then you get your phase, then you just plot it out for the magnitude versus the frequency and phase versus frequency. We also introduced the integrator and differentiator and applied these things right here to the classic feedback system, where here's like your open loop gain right here. Here's your feedback amp right here. We also looked at gain error, okay, and also fractional gain error. And we started to introduce the non-ideal, looking at a finite open loop gain and also a non-zero internal resistance right here. Okay, so for the new concepts, we'll first examine how to do Bode plots by hand. Then we'll look at the input resistance, okay, from a non-ideal op amp. We'll do a summary of non-ideal inverting and non-inverting amplifiers. And then we'll look at different classes of amps, such as the series and shunt feedback circuits. These include the voltage amplifiers, which is a series shunt feedback, transimpedance amplifier, which is a shunt feedback, current amplifier, which is shunt series feedback, and transconductance amplifier, which is a series feedback. Then we'll look at a unified approach of analyzing these things, and also introduce Blackman's theorem right here. This person used to work back in Bell Labs back in the 1930s, 1940s, but he has a very useful type of equation for looking at input resistance and output resistance of these amplifiers. Okay, so how to make Bode plots by hand. Okay, so we'll start with an example. Okay, so let's say here's your transfer function right here, and it has some zeros and poles. Okay, so the first thing you do is, if you're given your function like this, you want to put it into this form right here, where you have like 1 plus s over some frequency. Okay, so first what you do, you factor out all the numbers that are that are not, well, you factor out the real part, right? So that's a 10. You want to factor out that becomes 100. Down here you have a 200 and 1,000. So you factor out both of those. And so when you factor out the real part, it just means that the imaginary part is divided by the real part, right? And then you take that 300 divided by 200 times 1,000, and you group that all together into this value. So here's like your amplitude, your maximum value right here. And then you have these factors on the numerator and denominator. So your max amplitude, just by looking at that, is this right here. This value, converting it to a log, converting it to decimals, is negative 56.5 decibels. You see that you have a 0 on the numerator, so right here, and then you have these poles on the denominator here. So for the magnitude of h, what you do here is you take this value right here and converting this to log, basically these two, well, each factor is going to be added together, right? And so these two things are going to be added, these are going to be subtracted down here. So this part right here is just 20 log of that value. This is 20 log of that value right here. Those are added together. And then you're minusing the two things on the bottom, so it's 20 log, and then the magnitude of that minus 20 log magnitude of that. And then for each one of these, we'll see how to plot each one individually, and then you add up the entire thing graphically. For the phase, very similar, but you're doing tangent inverse of the imaginary part over the real. So this doesn't have any imaginary part, so that's why it's just 0 over the real part, plus this right here, which is the imaginary part over the real part, minus this part, which is imaginary part over the real part, and this part, which is imaginary part over the real part. And yeah, so when you look at the imaginary part over the real part, any factors are going to be canceled out, so that's why you have to worry about the ratios of those kinds of things. So just imaginary over the real. Again, these parts right here we're going to add together graphically and plot it out, as you'll see. So for this right here, this is a plot of just the magnitude. And so here's that equation that we had where we broken everything up into different parts that we're adding together. Okay, so taking one at a time, first you plot this part. And this is not a function of frequency, so it's a constant. So that's just a constant, negative 56.5 decibels. So that's this line right here. So you draw that on your semi-log plot. Okay, and that's 1. So for 2, right here, we'll do that in green. And if you were to plot this out, is this part right here. I'll try to explain that. So what's going on with this part is that if you, okay, so at the cutoff frequency of 10, right here, you have a magnitude of square root of 2, right? Because so you have 20 log of 1 plus j 10 over 10. So this is the part you're plugging in right there for the frequency. So that reduces down to just square root of 2. And this right here, if you did this in your calculator, I think it's about 3 decibels. Okay, so that means that at this inflection point, at a cutoff frequency of 10, that right there is that right there is going to be 3 decibels. So if you were to plot this out, you're going along this line, and then at this frequency right here, it starts going up like that. But really, you have this 3 decibels right there. So in actuality, it may asymptote to these values right here, but at that point, it crosses 3 decibels, like that. Then asymptotes to that. Okay? That's how to make sense of that part right there. Now, when omega is really small, like in this range right here, this is like a really small fraction, so it's less than 1. So the only value that really stands out is this 1. And so if you were to look at it as it gets close to 0, that right there is going to be 0. So that's why these values, like right here, when omega is really small, this goes to 0. And then as omega gets very large, then what happens is that this value dominates, and that one doesn't. So that's almost like it's not even there. And remember, it dominates per decade, so every decade is like an order of 2 larger. So for example, at the next decade, where omega goes to 100, you have 20 log 1 plus j 100 over 10. Right? Well, this piece right here is like 10. Right? And so if you look at 20 log of 10 as your magnitude, then that's just 20 decibels. So that's why a decade over, that's sitting right around 20. Okay? Now let's look what happens at, when that's 10, that's 100. Let's look at 1,000 right here. So when this value becomes 1,000, what happens is that, magnitude, this piece right here becomes like 100. And so 20 log 100, well, this is going to be 2, right? So that's like around 40 decibels. So that's why at that omega, then that should be around 40 decibels right here. So that's why, and of course you're doing this on a log plot. So that's why it looks like the asymptotes quite quickly. But that's why this goes off at 20 decibels per decade, because of these reasons right here. Okay, and then that's why this, when it gets really small, it asymptotes to 0. And the same thing happens to 3. So for 3, it had a cutoff frequency of 100, right? So if I put 100 there, that's going to be 1. And that means it is minus there, so it's going to be like minus 3 decibels. So it's going to be like just a little bit below this 0 point. But that's like the true curve, right? But it asymptotes to zero here, because when omega gets really small, like 10, 1, it asymptotes to a magnitude of 0. Then as omega gets large, like 1,000, well, if you have 1,000 over 100, then that's going to be 10. And then this whole thing is just going to be 20 decibels. So that's why you get 20 decibels. If you go to 10,000, then it's going to be 100, and then it'll be 40, well, negative 40 decibels, and that's where you get that right there. Okay, and you can apply the same thing to this one, right? Here's a cutoff, and then it asymptotes this direction to 0. It asymptotes this direction to this this line right here, this linear line. So once you have all of these, you have 1, 2, 3, and 4. Then you add all these up together, and then you end up with this summation curve right here. And this is the entire magnitude curve right here. So this is the one you want, right? So here, all these lines, the 1, 2, 3, and 4, they're all 0 right here. And this portion right here, you only get this line that survives, because that's everything else is 0 right here. Well, this is not 0, so the whole thing is lowered down to negative 56.5. Okay. So you got negative 56.5 plus all of these zeros right here. For here, you got 3 and 4 is 0, but that one is at 20 decibels per decade, so that's why that's going up. At this point, you're adding the green and this purple together. This is 20 decibels per decade. This is negative 20 decibels per decade. So they cancel out. So you get like this horizontal line right here. And then right here, what survives is the 20 decibels, the negative 20, and negative 20. right? So first you're having the 20, this red one cancels it out, then it's horizontal, and then you add this negative 20, then it goes like that. And then it keeps on going down like that. Okay. So anyways, that's the magnitude. So any questions about plotting this magnitude right here? By hand? All right, great. For the phase, very similar. So what you want to look at is each component as you plot. Okay, so for this first one right here, you had the imaginary over the real, so that's this one. And the inverse tangent of that, of 0, is going to be 0 degrees. So that's doesn't contribute anything. It just lies along this line. For the second one right here, you have to look at what happens to this tangent, to inverse tangent, when omega c is 10, when it's less than 10 and greater than 10. So let's see what happens when omega c is at 10. So when omega c is at 10, then the numerator becomes 1 divided by 1, so the whole thing becomes 1. So inverse tangent of 1 is 45 degrees. So at omega c, this is going to be 45 degrees here. Okay? And then as omega gets smaller, you have inverse tangent of a very small value. And so you could approximate that curve as this part right here, right, going to 0. And if you look at what happens when omega is 100, if you put like inverse tangent of this whole thing becomes 10, then you get something very close to 90. You get like 89 point something. And so that's like right there, like right below that inflection point. And then anything larger, like if you put 100 there or 1,000, then that gets to 90. All of that right there. Okay, so it looks sort of like this sort of like a semi-S shape right here once you finally plot it out. But that's how you get that curve. But it also means this: at every cutoff right here, you're going to get 45 degrees for each one of them. So that means when you plug omega c equals 100 right here, this argument is going to be 1. So it's going to be inverse tangent of 1, which is 45 degrees. So you're going to get, but it's going to be negative. So that'll be negative 45 degrees here. Same with 4. When that's 500, that's going to be 45 degrees right there. Okay? So the same thing. They start off at 0. They cross into 45 degrees a decade after that. And then a decade after the 45 degrees, they all asymptote to 90. Okay? Same with all of them. They cross 45, asymptote to 90. Same with this one. Crosses 45, asymptotes to 90. Okay? But then after that, then you add them all together. So you have the 0, you have the 2, which is this slope right here, which is 20 decibels per decade. At this part right here, you have to add this green one and this purple one together. So that they cancel out right there. At this part right here, you're adding in the red. That starts right here. And then from this part right here, this one goes to 90. So this component of slope goes away. And then these two dominate. So that's why the slope changes right here. And then at this part right here, the blue slope this purple slope goes away. So you have a change in slope here. And then right here, the red slope goes away. And then this blue slope continues flat like that. So it starts off like this, kind of goes around, and then it gets flat right there. Okay. So question about the phase? Okay. So let's see about this. So anyways, yeah, so that's how to plot by hand. And again, the thing is the only thing you have to worry about is just the transition from the asymptotic values, through your inflection point. But those are just estimates. Okay, so let's move on to infinite input resistance. So here's the kind of question we're going to be asking about these two types of op amps. So here's like an inverting kind, here's a non-inverting kind right here. And what we'll do is we'll look at the input resistance as seen from the outside. Okay? And of course, if you want to look at the input resistance of something, what type of thing do you do to that circuit to look at input resistance? Or even output resistance. What would you do to that circuit? Any guesses?
Apply a voltage.
Yeah, exactly. Apply some kind of source. It could be voltage, current. And then you look at the ratio of the voltage that you're applying versus the current that's being generated by applying that voltage. And then the ratio of that is going to be your resistance. Okay, so since we're doing at the input, we'll put it right there. So let's look at this one first, right here. And again, we're assuming it's not ideal, right? So the amplitude is going to be finite, and that resistance right there is going to be finite as well. But we are going to assume that this feedback current right here is much, much less than, let's say, this current right there. So we can approximate that as about being 0. Okay, so this is what we're going to do. We are going to apply this voltage Vx to this, okay, and we're looking at the resistance looking into that op amp in that direction. Okay, so so in this case, we're going to assume that this this I negative is much, much less than I2, and that means that I1 is about equal to I2 going in this direction. Because very little bit of this I2 is going in off in that direction. So so here are the equations, and so basically, just applying Ohm's law right here for Ix is just this Vx minus V1 over RID. So here's Vx we're starting from. This voltage right here is R1, which is right here, and that's the resistance passing through. And so the kind of things that we need are R1, this V1. We plug it in here later, but we have to obtain it down here. So looking at what V1 is, so V1 right here is going to be I1 times R1 right there. Okay? That's the voltage, because that's 0. So any current going this direction is this voltage drop going right there. Which also means that I2, V1 also equals I2 R1 because these two currents are the same. Okay? And so what we can do is plug in what I2 is right here, which is VO over R1 plus R2. Okay, you guys see that? So this current I2, which is going all the way through the whole thing, is a voltage drop from V0 to 0 divided by the entire resistance, because no current is going off in that direction. That's where we get this from. And then we'll identify this as being our feedback gain right there. And this VO right here, that voltage is just this voltage right here. So we plug in the amplitude, the gain times the VID across here. And VID is the difference between these voltages, right? And so then we get this value right here, and we associate this as being the loop gain for T. And this is the part we plug in to this V1 right here, in parentheses. And then we factor out the Ix, and then for this Rn, it's just Vx over Ix, which you get this value. Okay. So looking at this non-inverting amplifier, it looks like the resistance looking into this is just the resistance across these two terminals right here, being multiplied by your loop gain there. Okay, now for the inverting op amp, we'll look at two. We'll look at one without a resistor right here, and then this one with, we'll look at this one without a resistor, and the other one with a resistor. Okay, so for this right here, well, from this case right here, where I1 using ACL is just equal to I minus plus 2I. So I minus going this direction, and I2 going in this direction right here. So I minus is just V1 over RG right here. And I2 is, the voltage is V1 minus V0, V1 minus V0 over R2. Okay? And then we identify this V0 as being A V1 right here. And then, so here's the gain. And then inverting that, we can see that this resistance right here is going to be these two resistors in parallel. Okay, that's where I got that from. Now, if we add a resistor onto that, then the only thing that happens is that, as seen from the outside, where this resistor is included with the op amp, then it's just like adding a resistor in series with this resistance of having this in parallel with that. Okay, the difference between here and here. Okay, so here's a summary of the things we just looked at right here and the things we started off with last lecture. Okay, so this is for the inverting and non-inverting amplifiers. Okay, so this column is for the inverting, here's for the non-inverting. As you can see, for the input resistances, we just figured out this right here, this part. Here's what we get for fractional error, right here, gain error. Here's the output resistance. Both those are identical. And here's the voltage gain for both of those. Right there. Okay, so now let's look at series and shunt feedback circuits. Okay, so we'll go through each one of these. But in summary, you have these certain kinds of feedback types. You have a series shunt, and that type of amplifier is usually used for amplifying voltage. You have a shunt, and that's typically used for if you need a transimpedance amplifier or a shunt series, you need a current amplifier, and in series, if you need a transconductance amplifier. And here are all the gains in that right there. Okay, and we'll be using these suffixes right here. This V for voltage, TR for transresistance, I for current, and TC for transconductance. Okay, so it says here, when applied to an amplifier port, series feedback generally increases the impedance level. Okay, and shunt feedback decreases the impedance level. Okay, so that's what's called the shunt. And basically, a shunt is a device which creates a low resistance path for current to allow it to pass around another point in a circuit. Okay, so that's why it's like if you need to decrease impedance level for certain reasons. And it really depends on your application. Sometimes you want a high impedance level as input, sometimes you want low. Okay, so let's look at the various types. Here's an example of a voltage amp, and this type of amplifier is a series shunt. It has series shunt for feedback. And so I'll just read this. A voltage amplifier should have a high impedance resistance to measure the desired voltage and a low output resistance to drive the external load. Okay, talking about here and here. So to achieve the desired behavior, input ports of the amplifier feedback network are connected in series, and the output ports are connected in parallel. That's the shunt. So here's the basic form of that. For the next type, that's the transimpedance amplifier, and that's this type is called shunt. Okay, so a transimpedance amplifier converts an input current to an output voltage. Thus, it should have a low impedance resistance to sink the desired current and a low output resistance to drive the external load. To achieve the desired behavior, the input ports of the amplifier and feedback network are connected in parallel. That's a shunt. And the output ports are connected in parallel. It's also a shunt. So, shunt. Okay, the third type is called it's a current amplifier. It should be shunt series feedback. A current amplifier should provide a low resistance current sink at the input and a high resistance current source at its output. So that means the input ports of the amplifier feedback network are connected in parallel, and the output ports are connected in series. That type. And the last and fourth is a transconductance amplifier. This is a series type of feedback. So the transconductance amplifier converts an input voltage to an output current. This amplifier should have a high input resistance and a high output resistance. So the input ports and output ports of the amplifier feedback network are connected in series. Okay, and that's what that form looks like. Okay, so let's move on to a unified gain, and we'll apply this to our types of op amps too. So in all those cases, there's a way to look at all of these things. So for this loop gain, remember that's T, and that's this the open loop gain right here, and the feedback gain beta, and so T has an important role in determining these kinds of things: the gain, the input resistance, the output resistance, and even though we haven't done this part yet, we'll do that very soon. It has to do with the stability of the amplifier feedback. So it all has to do with the loop gain T. Okay, so for this closed loop analysis, here's one way to overall look at this thing for gain. Is as you can see, it's a function of this loop gain T. So you have the amplitude of the ideal situation. This X right here corresponds to our various types of amplifiers: the voltage, trans resistance, current, and transconductance type that we just talked about. And here's like them all together right there. So for all of these, you can apply this to any one of those right there, and that's how you determine the open loop gain. Okay, and so I just want to introduce the Blackman's theorem, but it's a very useful type of resistance formula for determining the resistance of the input or output of different amplifiers. And so here's the form it is right here. This X, you just replace it with in or out. So if you're looking for the input resistance, you can calculate that quite easily by applying this formula, or even the output resistance as well, saying R out is whatever that is. So what this Rx is the resistance of the closed loop amp looking into its ports is any terminal pair. Okay, what RD is the resistance looking into the same pair of terminals with the feedback disabled. Okay, and what this this TSC is, the short circuit, is the open. The loop gain with a short circuit applied to the selected port, and this right here, the open circuit, this TOC is a loop gain with some port, with the same port open circuited. And so how you apply this is first we select the port where the resistance is to be calculated, and then next you select a controlled source in the amplifier's equivalent circuit and use it to disable the feedback loop, and also as reference to find this TSC and TOC. Okay, so what we'll do next time is we will go through some examples when we actually apply this. I just want to introduce it here. And we'll be applying it to the different kind of amplifiers that we discussed today. All right, so any questions about this stuff today? Any questions about the homework? Oh, good then. Okay, so I didn't give you guys homework for Wednesday, so I'm going to do that today. We don't meet on Monday. So I think the homework that I gave you today for Wednesday, that'll be due on Tuesday evening, and then the homework for this lecture I'm going to give you guys, that will be due like the Wednesday after that. Okay. All right, that will end, and see you guys on next Wednesday.